Well, good morning, everyone. I hope you had a good Pi Day yesterday. Today we're going to talk about distances and the tangential velocity that all the flat earthers like to jump on the bandwagon for. Here are some of my irritating statements that I hear all the time. First of all, there is no curve, and I think the last video we proved curvature without a doubt. If you haven't watched that, go back and see that one. The next thing they say is there is no rotation. What they're actually talking about is tangential velocity, and we'll talk about that today. And the next thing that you hear a lot is the flat earth distances are just the way they should be, consistent, and that we're all wrong. The next thing that just chaps me is that there's no scientific proof. Well, I'm going to show you some clear scientific proof of these things, okay? So the purpose of part 2 is to check the statements B and C with observational data, very easy to measure and calculate, and all of these things are intertwined with much of that data in use every day. So of course, for our scientific method, we have to have hypotheses. H naught is always, in statistics, it's always the status quo, that the Earth is a rotating sphere. The alternate hypothesis is that the Earth is flat and motionless. So now we're going to look at data, and this is just kind of a recap from last week, a little bit of a review. I wanted to collect data for many different cities across the world, and we used timeanddate.com. So I chose cities from as far north as I could find to as far south as I could find. The data that we have, if you remember, is North and South America, Europe and Africa, and then finally Asia and Australia. And I'll show you that on a map. And of course I replaced that one point. Latitude and longitude I took from another website, dateandtime.info, and it was corroborated with several other websites. I just wanted to make sure I was getting the right latitude and longitude. Here's the map, and you can see the North and South America cities right here, starting up at Alert, down to Punta Arenas. And this one right here is the one that I deleted. Europe and Asia, or I'm sorry, Europe and Africa are those, and then Asia and Australia are those. And of course, more review. I took all this data from timeanddate.com, sunrise, day length, solar noon angle, each for spring, summer, autumn, and winter solstice and equinox. So here's where I did the calculations. First of all, for calculating tangential velocity, Cities were chosen in pairs. They have to be across the same latitudes because obviously the sun is moving, or we observe the sun at moving east to west. So from what I have 11 pairs of cities. This was the hardest part. It took me forever to get it straight. Sunrise times had to be changed to UTC, Universal Time, and I had to take into account daylight savings time. Those were things I didn't realize at first. And then I found out later, which I had never known, Simon Dan. I never knew that daylight savings time was the opposite in the northern hemisphere, and backwards from that in the southern hemisphere. What a surprise from a northern hemisphere guy. Measured distance I just got that from questioning Google. I just put a question in, what is the distance between city A to city B? Calculated distance and flat earth distance. Both of those I took from Walter Bisland's calculator. You can find it at that website right there. It's a pretty interesting place. Also, I calculated tangential velocity. This was the very simple everyday equation. Velocity equals distance over time. Everybody knows that. So for distance, I used measured distance, obviously what I considered the corrected distance. For time, I subtract time for the from city, from sunrise, to the time for to city, and converted that to elapsed time. The estimated tangential velocity using cosine. This was a calculation for a perfect sphere. It's calculated from a known tangential velocity, which everybody quotes all the time. Mr. Dan Pratt all the time. 1,037 miles per hour at the equator. If you multiply that times the cosine of latitude, you'll get a range of velocities ranging from the equator to the pole, and we can use that to compare to my calculated value above. And then percent error, I just calculated that as the usual tangential velocity. I don't know where that AL came from, but a standard comparison value. All I did is use the regular percent error comparing these two just to see how far off I am. And then here's my table. This should show you all what we got going here. So here's the table. You see over here is my from city down to here. Latitude, longitude, sunrise times, and these are for the summer solstice. So I took sunrise time there. If you look at my last video, the times are different because I converted to UTC. Okay, then I have the same data for the two city, which are these down to there, latitude, longitude, the sunrise time converted to UTC. Here I have the measured distance, and again I got those from Google. The calculated distance and the flat earth distance I got from Walter Bislin's distance calculator. Both of these distances are compatible with what I expected to see, so that's why I can pretty well trust that those are correct. The calculated tangential velocity is next, and then the estimated tangential velocity for a sphere is this next column, and then the percent error is the last column. So let's look at the data a little bit. Let's see, these two cities right here, Quito and Kinshasa, are right on the equator. So you can see Quito is 0.2 degrees off of the equator. Kinshasa is 4 degrees, so they're pretty close to the equator. And if we look over here, the measured distance is 6471. The calculated distance from Walter Bislin is also 6471. For Kinshasa, it's 8984, and Walter Bislin says it's 8992. Okay, so flat Earth distances, and this is from the pole to the equator, and that's 9,308 miles for Quito and 12,237 miles for Kinshasa. I just realized that I misspoke on this. The flat Earth distance is the distance between the two cities. So it's not from the pole, it's between the two cities. So now if we compare the measured distance to these two calculated distances, which one of those seems closer to the measured distance? And obviously, since they're equal, you can see that the calculated globe distance is more correct than the measured flat Earth distance. And we can do this for all of the pairs of cities. You look up here at New York to Valletta. Valletta is on Malta Island, so they have close to the same latitude, a little bit way different longitudes, so they're way far apart on the map. And if you look at the distances, actually the distances are very close. So 4608 is the accepted distance. 4597 is the calculated distance, and the flat Earth distance is 4991. We expect those to be close because obviously on the AE map, the northern hemisphere is closer to the actual value. But anyway, we go to the calculated tangential velocity. This is what I calculated from observed data. I got 864 miles per hour, and the estimated for a sphere is 840 miles per hour, so that's barely 3% in difference. So you can see, I think, that calculating the velocity, or rotation as flat earthers like to call it, is very close to what a perfect sphere would be. And again, let me reiterate that this is because this change from the equator to the pole is because it's a sphere. As you move further north and further south from the equator, you have less distance to go in a day, so that you expect tangential velocity to be lower. I wanted you to notice for Hobart and Port Williams, Chile, these are very far south data points, and I noticed here that the measured distance and William Hobart's calculated distance were pretty far apart, even though the flat Earth distance is like incredible. I mean, it's more than the circumference of the Earth. When I suddenly realized that if you add those two numbers together, 5370 plus 8647 is equal to 14,017 miles. Coincidentally, if you calculate the circumference of the Earth at that latitude, you get 14,168. So those are almost identical, and the reason is because in the measured distance, they go across the Atlantic Ocean. In his calculated distance, he goes across the Pacific Ocean. So that's why those are different. But even the fact that they're, quite a bit different, still looking at the flat Earth distance as 29,000, that's, incredibly different. So that's my velocity differences. I think you can see clearly that the movement of the sun from east to west more closely fits the globe model than it does the flat Earth model. Just real quick, I want to mention down here, these are some calculated values for radius and circumference for both the globe and the flat Earth. I just want those for comparison. Especially take note of these last two at the bottom. Next week, I got a real surprise for you about these two numbers. It will blow your mind, I guarantee. So let's look at the results. Again, the measured distance is very close to Walter Bisland's calculated distance every time. Flat Earth distances are larger than globe distances every time. And the further south of the equator, the further off they are. So if you go back to think about the AE map as a circle, everything south of the equator is just too far apart. So for the rotation, tangential velocity, We know at the equator it's 1,037 miles per hour. And you can see, like I said on the table, they're roughly 11% and 3% off of that expected value. For a perfect rotating sphere, I said before that tangential velocity should decrease by the cosine of the latitude, and you can clearly see from the table it's decreasing for increasing latitude, and the error is generally very low. It's very easy. This is for you flat earthers. It's very easy to calculate the tangential speed of the sun rotating around a flat disk, which moves from the Tropic of Cancer across the equator to the Tropic of Capricorn and back to the Tropic of Cancer. In order to do that and make it all the way around the Earth in one day, it's going to have to move at 1,200 miles per hour to 2,050 miles per hour. I can't tell you how fast that is. All you flat earth guys think this 1,037 is a big number. Here we go at 2,050. That's almost Mach 3 for a sun that is supposedly inside the dome and close to the Earth. We have a something that's moving at Mach 3 around the Earth. So in conclusion, it's very clear that distances match that of a near sphere. Tangential velocities clearly match that of a sphere rotating at a constant angular speed of 15 degrees per hour. And the increases and decreases with latitude are just like we expect. For the flat Earth, the circumference of that flat disk at the ice wall has got to be 78,143 miles. Now think about how large that number is. And then once again, it just blows my mind that the sun has got to move up to nearly Mach 3. And I can tell you clearly, there's no other way to interpret it from this data. The Earth has to be a sphere. So for further study, next week, I guarantee you I've got some surprising results for you about distances and areas. For part 3, we're going to look at day length. And for part 4, I plan to look at some data from winds and storms, prevailing currents and ocean currents. Once again, I think you'll be surprised. These are some of the websites that I used. Just give you a minute to look through those. Here are some of my favorite channels. Of course, Simon Dan, couldn't do it without him. Conspiracy Cats and Baldy Cats. There's nobody better for physics. Andy Flatter, you're a good guy and you make great videos. Wade's Underworld, same thing. He's giving you the personal observations that flat earthers always gripe about. Get outside and look at your observations. And then last, Rapid X, he makes some good music videos you'd like. So that's it for today, guys. We'll see you next week.